Okay. So,
Screen.
Where's that guy?
That's going on up there.
What?
Said you got a rat's nest going on up there with all those toys.
I know.
I'm sure it'll fix itself over spring break.
So the first thing we have to do is calculate the external loads. So free body diagram of the whole thing.
Use the soup. Oh, never mind.
I'm going to.
Oh, what? Ours doesn't say 45 degrees.
Oh, really?
Yeah, I'm looking at it right now. Yeah.
Oh, okay. Well, do you want to see it other than that?
No, 45 degrees looks good.
Yeah.
That's, yeah.
Or is that your only question?
Kind of, yeah. Like, I
Oh.
think I got it, but...
Let's do it anyways. Okay, so 45 degrees. And I'm going to assume that all the torque is provided over at the left instead of the pin and slot. Okay, so this pin joint over here, I'll call that RA, and there's an external torque, reaction torque, and then 2,500, and then 800 this way, and then I'll call this RB. You could be having this face either one of those two directions. And then we have to put the weight in. I've chosen the body to isolate, so I can just go right now to, instead of putting the weight as a distributed load, put it as a point force, 700 newtons. And so Newton's second law, we have RAX, RAY, plus 2,500, 0, plus 0, negative 700, plus this angle is at 45, so 0.7071 RB, 0.7071 RB is equal to zeros. So RAX plus 0.7071 RB is equal to negative 2,500. RAY plus 0.7071 RB is equal to positive 700. Then the moment equation about the z-axis. I'm going to put my about point here. So the first force going left to right that produces a moment is the 700. So we got plus or minus a moment arm of, this whole thing is 2 meters long. So a moment arm of 1 times 700, and that's a clockwise rotation, so we'll take the negative. And then the RB at the end, only the vertical component produces a moment there. So we have plus or minus a moment arm of 2 and a force of 0.7071 RB. The vertical component is upward, so that's a counterclockwise moment. So we'll take the positive.
Why is it RB and not RBX?
Okay, so this is, so a pin and slot joint is a force in a known direction.
Oh,
And so you're only going to represent it with a single, so you're going to figure out the unit vector, and then you're going to multiply it by a single variable instead of a vector variable.
it's a vertical component.
Okay, right. So this force is, well, I guess I wrote it here. So this force vector is represented by this way, this way. The only variable is RB, but you have X and Y components. And it's only the Y component that produces a moment. The X component is just right along the beam, and so it doesn't cause a rotation. And all this is equal to 0. So our third equation says 1.414 RB is equal to 700. And then the moment equation about the x-axis, we have our TR in the positive direction, our 800 in the negative direction. So TR is equal to 800. And then we can solve this system. So we have RB is equal to 495.05, and RA I get negative 2850.05 for X. And 349.95 for Y. Anyone disagree about that? No, because you didn't know what the angle was. So now we can go to the internal loads. And how many cuts do we need? Well, remember, always be careful that this weight force, for this calculation, we treated it like it happened at the center. But remember, that's really a distributed load, uniform distributed load. So if these two things weren't here, don't make the mistake of thinking that this weight force affects the number of cuts you use. But these two things are here, so we have to do a cut at the, we have to switch our cuts at that center anyways. So cut 1.
350 for the Y. So
Yeah. So cut 1 goes from x's from 0 to 1. And I'm going to first draw it with all of the distributed load in there. So we have a torque this way of 800. And then we have a force vector of negative 2850. Yeah, I'm just gonna change these to negative 2850 and 350 And then we have our weight. Okay, well, this thing is 2 meters long, and the total weight is 700. Yep.
So we're pretending like the pin can't have an effect on the rotation of the.
We're pretending that the pin in the slot does not have a significant effect on it, yeah. I mean, really, I should probably tell you that. I mean, it's sort of on a case-by-case basis, but since this thing has enough looseness for this thing to slide, it's not going to apply a torque likely as well as this one will. Okay, so this is 350 newtons per meter. And then we have our internal loads, T, V, M, fancy T. Yeah. And for the uniform distributed load, we have a length of this rectangle of X, a height of 350. The centroid is right in the middle, and the area is 350X. So now I'll redraw this free body diagram with the equipolant point force. So we have the 800, the negative 2850, and positive 350. The weight force at the center of 350X. And then the internal loads. Newton's second law says negative 2850, positive 350, plus 0, negative 350X, plus T, negative V, is equal to zeros. So T is equal to positive 2850. V is equal to negative 350X plus 350. Then the moment equation about the z-axis. We have a moment arm of x over 2 for the weight, and the magnitude is 350x, and that's a clockwise moment, so it's negative. And then we have plus m minus vx is equal to 0. So m is equal to vx plus 175x squared. And now plug in v, and m is equal to, so the negative 350x squared plus the positive 175x squared comes out to be negative 175x squared. And then plus 350x. And then the moment equation about the x-axis. We have the positive 800 and the positive fancy T. And so the internal torque is negative 800. And let's do the derivative checks while we're here. dm dx. That'd be a good rapper name for a rapper who raps about math.
I agree.
He'd be super popular with all the kids.
What about DJ DX?
Yeah, that's his DJ. So this is negative 350 x plus 350, and that is equal to v, so that's good. And then negative dv dx is negative 3, well, the negative makes it 350, and that is our downward distributed load function. So those all work out. So that gives us some confidence about that. And now we'll go to cut 2. I'll be right back. This is for x values from 1 to 2. So we have the force over here of negative 2850, positive 350. The torque of 800. This time we're past the middle, so we also have the 250 and 2500 and the 800. So we have a force of 2500 like this, a torque of 800 like this. I'm going to redraw this. So there's the 800. Then we have the distributed load. Of 350 newtons per meter. And then the internal loads. And the distributed load works the same way as it did in the other cut. We have a height of 350, a length of x, centroid in the middle, an area of 350x. And so I can redraw this. So we have the force of 2500 here. The torque of 800 here. This time we have a weight force that we're treating as a point force right in the center. And then we have the internal loads. So Newton's second law says negative 2850, 350 plus 0, negative 350 x plus 2500, 0 plus t negative v is equal to zeros. So T is equal to 350. And V is equal to negative 350x plus 350. the moments I'm going to do around this point. So the moment equation about the z-axis, we have that weight force, that 350x, has a moment arm of x over 2, a force of 350x. It's down, so that would be a clockwise moment, so negative. And then we just have plus m minus vx is equal to 0. So m is equal to vx plus 175x squared. Plug in for v and you get that m is equal to negative 175x squared plus 350x. And then the moment equation about the x-axis. You have 800 minus 800 plus t is equal to 0. So the internal torque on the second half is 0. I always, I'm usually pretty much always in the habit of making a dot where I'm using my about point for my moments about z, and even though I always do it at the same point, just because it makes the math simpler. For the moments about x, how come I don't ever think about what the about point is going to be?
Because it doesn't create a moment.
Is it couples?
Because they're all couples. So when I'm doing the moments about the x-axis, I'm adding up things that are always couples. It would be different if I had, if I ever gave a problem that was like, here's your beam, and at this point we have like a platform where this force is applied, Okay, then that wouldn't be a couple. That would just be a moment produced by a force. And then we'd have to decide, like, okay, maybe the about point is the axis of rotation, or we could decide wherever we wanted,
Could you just represent that as a couple and kind of forget about that little platform?
Well, I mean, it would have that effect, but you'd have to sort of think that through. I mean, you could do it that way, but you'd have to think it through. I mean, the thing is, you also have these forces acting over here that are along like a center line or whatever, So anyways, there are ways to do it where you would have to think about an about point, but since we just always have them drawn as couples, that's why the about point doesn't matter. For a couple, an about point doesn't make any difference, remember?
But I guess like all these couples really would just sort of be like representations of a moment.
Yeah, remember
Like
that
you can't really like just magically produce a couple.
as a moment.
Right.
Right. Yeah, don't make me go through the derivation again. Remember the derivation from statics?
I remember doing it.
Where I show, like, where you can show quick and easy that that the dependence on the about point goes away.
Mm-hmm.
And since a couple is always equal and opposite forces, the forces go away too. And so
it could be here or here or here.
Yeah, but since they're equal and opposite, they always cancel each other out. So the forces don't matter. The about point doesn't matter. So you can always just treat it like a moment that you add on. And you know, the way it works is, like Chase, you were saying, you know, think about it as like, this is like has a hex shape or whatever, and you're turning it with a wrench, you know. That's my worst drawing in a while.
Of the day.
Of the day for sure. Okay, but like, so when we're applying, when I draw like an external torque, you can think of it like that. That's one way it could be applied. So how is that a couple? And the answer is that you're applying a force. So if you're turning it this way, you're applying a force on one corner like this, and a force on the opposite corner, equal and opposite like that. And you're not really doing it just at a point, so you're really producing a profile of equal and opposite, distributed loads they're equal and opposite forces that cancel each other, and they don't have an about point because they're equal and opposite.
So it's kind of the same with like a screwdriver. Too.
Yeah, a screwdriver is exactly the same thing. So like if this is the slot of a screw, thanks. And you turned your screwdriver too hard if your screw looks like that. But yeah, if you're tightening the screw, you're just applying forces like this. And since each one of those is a pair of equal and opposite forces, the net effect is no vertical force, but just a pure moment. Any other homework questions you want to see? Let's stop.
Okay.
Okay. So spring break. And then, a week from Monday, we will start calculating stresses due to internal loads. Yeah.
Are we doing exams after we're back